Hello fellow CNC nuts and welcome. This episode is a natural progression from the last one. In the last one we squared up our gantry, but now we need to make sure it's properly calibrated. Now if you watched last episode you would have seen me check the calibration on my machine using nothing more than a sharpened dowel and some masking tape. And we'll be doing that again here. Now while I did show how to check it, I didn't show how to adjust the calibration if it was incorrect, so we're going to look at that. For that I used some basic steel rules. I have a 600mm one here and I've got a 1 meter rule there. So we're going to use that for the measurements. Now if you want to know how I made this sharpened dowel, then have a look at last week's episode. You'll see how I made this here in the spindle. Now when it comes to doing the Z, of course, these rulers here really aren't much use. You're not going to get an accurate measurement with them. So for that, we're going to try a basic digital caliper, which I'm sure most of you have laying about the workshop. And to hold it vertical, I've just taken a piece of plywood here and I've just cut a little slot into it so the caliper can slot into it like that and it'll be able to stand vertical. Now the other way of doing it, and should be more accurate, is this one here using a dial. Dials are incredibly sensitive, so that's one method. And also if you have a stand like this here, you may be able to use that on your machine. Okay, now the good thing about it is my machine is a mixture of rack and pinion and lead screw, so we'll be able to look at both. And one of the first things we need to do when doing this is we need to do some calculations. If you're going to start off from scratch and don't know what figures to put into your machine, you're going to have to calculate them. And they alone may get you as far as you want to go. It's entirely up to you, but I would definitely recommend going further and doing a manual calibration. We're going to start by looking at the X and Y axes on my machine. And we'll do some calculations for that. My X and Y use rack and pinion, which look very similar to this. In actual fact, it is actually this. I ripped this off the machine. And we need to calculate each part of this here to work out how many steps we will need to move this here 1 unit of measurement along our axes. Now by unit of measurement I mean if you're using imperial, then you'll need to know how many pulses it will, how many steps it'll take to move this here 1 inch along your table. And if you're using metric as I am, you need to calculate how many steps it will take to move this here 1 millimeter along the table. Now this isn't the problem. In fact, we need to calculate one to get to the other in my case, because this is an imperial unit, so I need to calculate everything in imperial first and then convert it to metric. So let's start with the first part of it, our stepper motor here. We need to know how many steps it takes to make the stepper motor turn 1 revolution. Now I know from the specs of this stepper motor it's a 1.8 degree stepper motor. Now that means each step will move that motor 1.8 degrees. So when you have a stepper motor similar to this here and you turn it, you can feel the individual steps of that stepper motor, and those are known as full steps, and the spec sheet will tell you how far that shaft is turning for those. As I said, mine is a 1.8 degrees. Now for this type of thing a calculator is indispensable. So we'll just clear that there, and we're going to have 360 degrees, which is a full revolution, and we're going to divide that by our 1.8 degrees that each step of that stepper motor takes, and we come up with a figure of 200. So 200 steps, and that stepper motor will have done 1 full revolution. But that's not quite the full story. That's 200 full steps. In this modern day and age, all stepper motor drivers use micro stepping. Now what that means is it puts steps in between those full steps to give even more accuracy. That's probably not quite true. part steps, half steps, or micro steps are not very accurate. The full steps are accurate, the micro stepping so-so. But the more micro steps you have, the smoother the stepper motor will actually run. A stepper motor run at full step sounds terrible, but run it in micro stepping and it sounds really nice and smooth. But positioning wise, only full steps are accurate, micro steps are close enough. So we need to know how many micro steps our stepper motor driver has. Now some have 2, 4, 8, 16, 32, 64, and I've even seen them up as far, I think, as 128. I don't use any of those. My Gecko G540 uses 10. So it takes 10 steps, or 10 micro steps, to get to one full step. So we had 200 steps to do one full revolution before. We now need to multiply that by the number of micro steps it takes to do one full step. In my case 10. I come up with a figure of 2,000. So 2,000 steps to make that stepper motor do one full revolution. Now you'll notice on the rack and pinion drive here, there's a wee timing pulley, which is attached to another timing pulley via this timing belt. This one here is a third the size of this. This has to do 3 revolutions for this to do one full revolution. So that means it now takes 3 revolutions of the stepper motor for the output shaft here to do one revolution. So we were doing 2,000 steps before for that stepper motor to do one full revolution. We now need to multiply that by 3, and we come up with 6,000 steps will be required to get this to do one full revolution. Finally, we need to find out what's happening with this gear. Now the spur gear that runs along the rack has what's called a root diameter. All gears have them. And that basically is the point at which they mesh. And if you were pretending that those gears were nothing but circles rubbing up against one another, that would be their root diameter. That root diameter will be somewhere between the top of the tooth and the bottom gullet of the tooth. Be somewhere in the center there. And that's the root diameter of the gear. You can consider that point to be as if the gear was nothing more than a circle running along a flat surface. So in my case, the root diameter of the gear on my drive is 1 inch. So now we need to figure out if that gear was to do one full revolution, how far along the rack will it travel? So taking it back to the circle, a 1 inch circle, if you want to know how big its circumference is, or basically how far it will travel in one full revolution, you simply multiply the diameter by pi. Pi. So now we have all this information, we can do the final calculation. We'll do it for imperial first. So we have 6,000 steps required to turn the output shaft on my rack and pinion drive one full revolution. We need to divide that by pi, and then we need to divide that by the root diameter of our pinion gear, and in my case it's 1 inch, so I'll just divide that by 1, and there we have it, a final figure of 1,909.859 steps to move my axis 1 inch if I'm setting it up as an imperial machine. Next we're going to calculate it for metric, and the formula is exactly the same. So I've got my 6,000 steps we worked out earlier, divide it by pi, and then divide it by the root diameter of my pinion, but this time I'm going to measure the root diameter in metric. So I'm going to divide that by 25.4, which is how many millimeters the root diameter of the pinion is, and I'm left with this figure here, 75.191. And those are the figures that I'll be entering into my control software. In Mach3, I'm going to go to Config, then down to Motor Tuning. I'll then select the Y-axis, and under Steps Per, I'll enter the metric figure we calculated. That's 75.191.31178. I then go across to Save Axis Settings, go OK, then back into Config and Save Settings. In UCCNC, I'm going to go to Configuration and select the Y-axis. Under Steps Per Unit, I'm going to enter the imperial value we calculated. In this case, 1909.859319. I then go Apply Settings, Save Settings. So as you can see, it's really very easy. All you need to really know is the root diameter of your pinion. You don't need to know how many teeth it's got. You don't need to know what pressure angle they are. None of that information counts, only the root diameter. You also need to know if there's any gearing involved, as there was between my stepper motor and that pinion, and factor that in as well. Also your micro stepping, of course, and the number of degrees on your stepper motor, but all these things are easy to find. Now, if you don't know what the root diameter of your pinion is, don't panic, just take a rough measurement of it, work out what you think it is. It'll be somewhere between the top of the tooth and the bottom of the tooth, just across the gear, and just use that to calculate it. That will get you roughly right, and then we can sort the rest of it out when we do the manual calibration once your machine's up and moving. Okay, well, before you guys lose the will to live, let's look at the Z-axis. Now, in my case, mine is lead screw driven. So that's probably what most people have got for their Z-axis, and even their X and Y. Now, ball screws are even better, and they're all calculate up at the same. All we need to know is how many turns per inch your lead screw is. Now, that's not to be confused with TPI. TPI is threads per inch, and there's a subtle difference between threads per inch and turns per inch. So here is a standard piece of threaded rod. It has 10 turns per inch and 10 threads per inch, which means if I was to measure down 1 inch and count how many times that thread crested in that 1 inch, I'd come up with a figure of exactly 10. Okay, here is a piece of lead screw of my machine. This here is 8 threads per inch, but it's actually 4 turns per inch. And the reason for that can be found on the end. I ground the end of this lead screw flat, and then I coloured the side here yellow, and this side red. They are 2 entirely distinct threads running down here. So while there are 8 threads per inch, there are 2 threads running in it. If I was to run my finger down each of those individual threads, the 2 would never meet. They're 2 entirely separate threads, which effectively means that they are travelling twice as far as a single start piece of threaded lead screw. So 8 threads per inch divided by the number of starts, in this case 2, means we have 4 turns per inch. And lead screws come in different threads per inch and different numbers of starts. So if you had a 10 thread per inch lead screw with 2 starts, you would have 5 turns per inch. And if you had a 10 thread per inch lead screw with 5 starts, that would be 2 turns per inch. So you do need to figure that out. You need to know exactly how many turns it requires of the lead screw to travel 1 inch. Or if it's a metric lead screw, how many turns are required to travel? 1 millimeter. Okay, so it's time for the trusty calculator. So let's start at the top. Stepper motor, 1.8 degree stepper motor, so we've got a 360 degree for 1 full circle. Divide that by 1.8 degree per step. We've got 200 full steps for this to do 1 revolution. Now of course we mustn't forget our driver here, microstepping 10 times, so multiply that by 10 and we've got now 2,000 steps for this here to do 1 full revolution. Now we need to turn my lead screw 4 times for this to move 1 inch, so we need to multiply that by 4. And there's the final value, 8,000 steps will move this 1 inch. Okay, so that's all very well, but I'm using metric for mine, so I can't go putting 8,000 into my machine. I need to divide that by 25.4, which will convert it to metric, and I come up with a figure of 314.96 and a bit more steps per millimeter, which is my unit of measurement. So that's what I would put into Mach3 or UCCNC. Okay, well what we need to do now is enter those figures, and then we can give it a real world test and just see how accurate that really is. But first I think I better reassemble my machine. I'm going to be using the same method we used in the last episode to check the calibration and to recalibrate this here. Now that uses a piece of masking tape with a cross printed on it, and the trick is to put the cross on the masking tape here first and slide it under the pointed stick in the spindle, rather than actually trying to draw the cross under the stick or even position the stick over the cross. It's far easier just to have it pre-done and slide it under. So quick, so easy to do. Okay, so what I've done now is I've got this point here. I'm just going to mark this as X, Y and Z0, and then I'm going to run the calibration on my control software. Now I'm going to show you how to do it in both UCCNC and Mach3. They're both virtually identical. To do manual calibration in Mach3, we come up here to the Settings tab and go down to the Set Steps per Unit. Now we select our axis we want to check, and I want to check the Y-axis, and I'm going to go OK. Now it brings up this box, how far would I like to move the Y-axis? And I would like to move it 1,000 millimeters, but because I set the Y0 at the back of the table, I'm going to make that minus 1,000 millimeters, which will bring it towards the front of the table. And I go OK. That now brings the axis forward here, and when it stops, we'll take our measurement. So for that, I'm going to take my 1 meter long ruler, and I'm going to put it on the cross at the start, and just put it up against the end of my pointed piece here, and just check what measurement it comes up with. And here we have a measurement of 999 millimeters and a half. It's not quite 1 meter or 1,000 millimeters. Mach3 comes back with this box here saying how far did the Y-axis move, and I need to enter the measured value, which in my case is 999.5, and simply go OK. Now it comes back with a newly calculated value for steps per unit. Would I like to accept this? Just go yes, and it's now adjusted my Y-axis. What I'm going to do now is I'll just move the ruler out of the way. I'm just going to hit go to origin point. That'll take it back to the start, and we can rerun this test to make sure it's now moving 1,000 millimeters. Now having done this, the chances are, and it is the case, it did not go back to the original point here, because I've now changed the measurement, unit of measurement there. So that's good. Reposition my starting point. We'll rerun the calibration test. And I'm now going to say that's 999.75. It's getting closer, so I'm just going to re-enter that figure, let it recalculate, run the test one more time. It's well worth taking your time to do this and get it right. We're relying on a long measurement to give us accuracy. So by using the longer measurement, we get more accuracy when we're doing this. And that's exactly 1000 millimeters. We can do exactly the same for the x-axis, and that'll be that calibrated. Now when it comes to doing the z-axis, a ruler really isn't the best tool for measuring movement here. There are devices such as this here, a set of basic digital calipers, that are designed to measure small distances accurately. So this would be a great way of measuring the z-axis movement. You can read the final results straight off the dial and input it either into UCCNC or Mach3 for the calibration, and hey presto, you're all sorted. So for using this here, I came up with this here. It's just a piece of wood with a slot in it. It's going to allow the calipers to stand upright like so, and then we can just simply raise it up until it just sits under the clamp on my spindle. I can then bring the spindle down using the calibration tool, get my measurement of how far it's actually gone, and enter the result into my control software. And that will sort out the calibration there. It's a really simple and accurate way of doing it. Even more accurate is the use of a dial. And for that, I've machined up a piece of steel here to go into the dial's clamp, mostly because I didn't have any 10mm steel shaft laying about. And it goes straight into the spindle. I can put the collet on here and wind it into the spindle. I can then move the spindle up and down and take my reading off the dial here. Now the advantage of the dial is it's very accurate and repeats very nicely, and I can move up and down and take my readings up and down, which I can't do with the digital calipers. The disadvantage of it is it only moves, in this case, for this one here, 1 inch at a time, or 25.4mm. But these things here should be very accurate, so I would prefer to use this personally over the dial. Now just one word of warning, you can't use the dial this way up. You never get the same reading twice. The spring, or at least on this model here, isn't good enough to bring it back to the same place each time. Now I had actually originally planned on using this here, which is the standard magnetic clamp that comes with the dial, but unfortunately there's absolutely nothing magnetic around here to stick this to, so I had to give that up as a bad job. In the end, actually, using the spindle collet is the best idea, but you've got to have the right size collet to clamp the shaft. That said, I do, so let's have a look at them. So the first method I'm going to try is the digital calipers. I've entered in the values that we calculated earlier as the distance per unit, and we'll see how accurately it comes out. So I've got the digital calipers standing vertical up under here, with it tucked just up under the clamp here, so when as the clamp comes down it'll push the calipers down. I'll just zero that. Okay, it's pushed up as far as it will go, and it's been zeroed. I'll now run the calibration in my controller software, and we'll see what happens. I'm going to move it down 115mm. In UCCNC, to do the calibration, we come to Configuration, select Axis Setup, select the axis we want to do, in this case the Z-axis, and here we have the steps per unit we calculated earlier, and now we hit the Calibrate button. That brings up this box here. We have our starting position, which is where the Z-axis is currently sitting. We have the current steps per unit. We need to tell it how far we want it to move. In this case, I need it to move minus 115 millimeters, and we can specify the feed rate, which I'm going to make 500 millimeters per minute, and just hit OK. Well, that's 115.3 millimeters. At the completion of the axis movement, it comes up with this here distance measured unit. This box lights up and we can enter in our measured distance. In this case, 115.3. Then I can go OK, and it will recalculate a new steps per unit, which I can accept by going OK, and it updates it over here, and just go here, OK. Now, just as a word of warning, do not click OK again here. Click cancel. If you click OK, it will try and move another 115 millimeters down and will crash the spindle into the table. Well, there we are. I'm 114.93. That's 7/100ths of a millimeter out. That is pretty good. Let's see what we can do with the dial. Now, what I've done here is I've put the dial into the spindle, and I brought it out over the front of the tabletop here, because this is too high. This arrangement is too high to actually use over the actual tabletop itself. So I put a metal plate down here that I'm going to take my readings off of. Now, the other thing I've done is I've disconnected this here. That's the power cable to the spindle. I've also made sure I've turned the VFD off, and that's just to ensure that there is no chance at all of it accidentally starting up while I'm doing this, because that would be a disaster. What I'm going to do, I'm going to put it into a slow jog, and I'm just going to bring the dial down, and I want to get that reading so that it is sitting on the 0 point. And here I can see the backlash on my system, which is pretty much nil. So my anti-backlash nut is working fine, and the dial is now reading 0. So I'm now going to try the calibration again, but because this is a 1-inch dial and I'm running metric in my case, what I'm going to do is I'm going to ask it to move 25.4 millimeters, which is exactly 1 inch, and we'll see what reading we end up with. Okay, so now that it's moved down the 25.4, I can see that I'm 1, 2, 3, 4, 5, 6, 7 divisions away from where I should be, and that is 0.0035 of an inch. So I need to do a bit of a calculation and work out how many millimeters that is, so that I can enter that into my software. So 1 inch minus 0.0035 is 0.9965 inches, and multiply that by 25.4. So I've moved 25.3111 millimeters. So I'm going to enter that into the calibration software. 25.3111. It's recalculated things for me. It's going to cancel that. Return to the origin point. And as we can see now, it's come up a bit higher than it was before. So I'm just going to now step back to the 0 point here. And we'll retest again. well, that about wraps it up for this episode. I hope you've enjoyed it and maybe learnt a little bit more about how to use that calibration functionality built into your machine. It's well worth taking the time to use it, even if only just to check that everything's right. Don't rely on the calculated values. They're going to be close, but I don't think they'll be truly accurate. And don't assume that because you're using the same components on your axes that they will have the same values either. Now the X and Y rack and pinion setup on this machine use exactly the same rack and pinions, but the calculated values at the end of the day were slightly different, and that's just because of the various tolerances of the rack and the pinion, and maybe other things as well. So don't take anything for granted, just give it a test and make sure it works as it should do. If you'd like to learn more about it, I will put a link in the description box below this video where you can go off to the write-up associated with this video, where I'll put any notes and anything else I might have forgotten as well. All that remains me to do is to thank you for watching. Don't forget to like and subscribe, and join me next time when I'm sure we'll have another adventure in CNC. Cheers! Crikey, it's cold out here. I can barely feel my feet, and it's only the beginning of winter. Mind you, it is after midnight, so I'm off to bed. Catch you guys later. Cheers.